Nous allons voir dans cette séquence comment
In this lecture, we will see how radiation interacts with the interstellar and intergalactic matter. Interactions occur at all spatial scales and are analyzed thanks to images and spectra, giving constraints on the physical conditions of the gas and dust in cosmic clouds. The interstellar gas, apart from the primordial hydrogen and helium, formed a few moments after the Big Bang, is created by successive generations of stars and is ejected into the interstellar medium after the death of high or low mass stars. For low mass stars, i.e., less massive than 8 solar masses, planetary nebulae are formed, while for the stars with masses exceeding 8 solar masses, a supernova explosion occurs, leaving spectacular filaments as shown in the figure. This image shows the Crab Nebula, Messier 1, that is a result of a supernova explosion visible even to the naked eye in 1054. Then, the gas is recycled into an interstellar medium in a galaxy like this one, Messier 51, where the hydrogen emission is well visible in the red in the spiral arms of the galaxy. The hydrogen emission is created by the ionized gas excited by the swarm of young massive stars visible in the blue in the arms of the galaxy. Apart from gas in galaxies, there is also dust that absorbs background radiation. This effect can be seen here in the form of dark trails through the arms of the galaxy. The background light is absorbed by dust. From this mix of gas and dust, new generations of stars, possibly associated planetary systems, are formed. Let's see in details what is happening in a nebula. The Carina Nebula shown here at optical wavelengths. Some sources of ionization can easily be identified, like in this place, a small stellar cluster, certainly composed of young hot stars. Another stellar cluster can be seen here. Those stars ionize the surrounding gas. The gas divides into protons and electrons. Possibly, they will recombine. Electrons fall back into the lower energy level, while at the same time emitting photons with a range of wavelengths. Each color indicates a different emission line, as it was shown in previous chapters. The density of the gas is very low, roughly 1 gas particle per centimeter to the third power, which gives P equals 10 minus 21 kilograms divided by m to the third power. There can be great differences in the densities from one nebula to another, from one galaxy to another. This density corresponds to the ionized gas that often produces emission lines. We find also dusty regions, similar to those shown before in the spiral galaxy. Dust absorbs radiation. In fact, this whole region is affected by dust absorption. Mass densities in this kind of region are even lower, about 10 to 13 particles per centimeter to the third power, which is 10 to 13 times smaller than the gas density. On the other hand, dust particles are much heavier because the dust is composed of atoms and molecules. The mass density is one of the order of 10 to 23 kilograms divided by m to the third power. This means that there is 13 orders of magnitude less dust particles than in the gas, but in mass density, dust is only 100 times less massive per unit volume than gas. All we said previously was about gas and dust in nebulae. Let's have a closer look at the Milky Way. So objects with much larger spatial scales, from this place to this other one in the slide, the distance is about 5 kiloparsec. On the previous slide, the scale was about tens of parsec. Here, the scale corresponds to the kiloparsec scale. The nebula that was shown just before has roughly this size, quite small comparing to the Milky Way. On the other hand, dust extends over a large region. Those areas correspond to dusty spots that absorb the light coming from the stars situated behind. Here are the other dust regions. In conclusion, the dust and the gas intervene at all scales. Let's take a look at what is happening with the ionized gas that recombines and emits radiation, creating something we can observe, nebulae. Here we will assume a gaseous nebula. composed of hydrogen, so as to simplify the calculations. Of course, the composition could well be different in this kind of cloud. Then, here is a ionizing source, stars. This ionizing source splits the atoms, of hydrogen in this case, into protons and electrons. They do not stay in this state. They will tend to recombine and emit light. Now, we will try to estimate the typical radius of a nebula, that is in a strong Gren radius, after the astronomer who calculated it for the first time. What we will try to characterize is this limiting radius of the nebula, the Strom-Gren radius. As always in science, there is an equilibrium. There are ionizing protons coming from the source, from the center of the nebula. Then there are electrons that recombine with the protons that were ionized by the radiation field. The flux of ionizing photons is equal to the recombination ratio of the proton-electron pairs. The number of recombinations is equal to the volume of the nebula, 4 divided by 3 pi times r 3, times the number of available proton-electron pairs. That is, Ne for electrons and Nh for protons. In this equation, there is also a constant that comes from quantum mechanics, and the origins of which is not needed to be known here. It is just a physical constant that is equal to about 3 times 10 minus 13 centimeters 3 times s minus 1. For a gas with a temperature around 8,000 Kelvin, which is a typical temperature for diffuse nebulae. We have calculated the recombination ratio as a function of radius, the parameter that we are interested in, and the electron and proton density in the nebula. Now, let's calculate the number of ionizing photons. For the calculations, we take a hot star as an ionizing source, with the temperature of about 45,000 Kelvin. This star has a black body spectrum, with its luminosity peak in the ultraviolet. According to the Wien law, lambda max is equal to 640 angstrom, which is in the ultraviolet part of the spectrum, where the photons carry a lot of energy, and so they can easily ionize matter. Here we have a nebula composed of ionized hydrogen. Before the calculations, let's recall a bit of nomenclature. We have talked a lot about hydrogen, so let's now present some notations. It may be that you are familiar with it, so treat it as a reminder. If you have such a notation, 1H, it stands for a hydrogen nucleus. A notation 2H stands for a deuterium nucleus. In this case, there is one extra neutron in the nucleus. Let's move on to the atoms. So we have now an electron that we will note as H1. This is an atom of neutral hydrogen. The electron in this atom is in its lowest possible energy state, with 13.6 eV. It means that in order to ionize a hydrogen atom, 13.6 eV must be delivered. In this case, one notes HII for the ionized hydrogen. Earlier, a notation H alpha, H beta, H gamma, etc. was shown. Pay attention not to confuse it with the notation that was shown before. Those are the hydrogen emission lines. We can also write H2, which indicates that two hydrogen atoms now form a molecule. So beware of all the different notations. That is all for the hydrogen nebula. Now, let's recall that we consider a single star with 45,000 Kelvin in the center of the nebula. The radiation peak is at 640 angstrom, and assuming that most photons belong to that peak, each photon has about the energy E gamma equals HV. Then let us imagine that all photons are indeed emitted at the peak. Thus, all photons have precisely that energy. The total amounts to 1.54 10 minus 5 J, which corresponds to 19 eV. Obviously, those are photons with an energy higher than the ionization energy, 13.6 eV. It means that if a star surrounded by hydrogen is considered, then, with a good approximation, all the hydrogen in the nebula is ionized because of the photon flux carrying an energy higher than the hydrogen ionized energy. Now, we assume that all the hydrogen is ionized, and so Ne equals Nh, and there is the same number of electrons and protons. This implies that the equation for the recombination ratio can be rewritten as a function of the hydrogen atom density, and it is equal to the photon flux, carrying an energy at least sufficient to ionize the atoms. Inverting this equation, we find the radius, that is, the limiting radius in the equilibrium, the Strömgren radius. It will be equal to 3 times the number of ionizing photons over 4 pi alpha times Nh square to the power 1 divided by 3. This is the equation for the Strömgren radius. It is given as a function of the following values: a physical constant, the density of the nebula, and the number of ionizing photons. The number of the ionizing photons can be estimated. In the easiest way, it is the stellar luminosity in the center of the nebula, divided by the photon energy. For a star with the surface temperature T 45,000 Kelvin, the luminosity is equal to 1.3 times 10⁵ solar luminosity. This implies that the number of ionizing photons is equal to 1 to 6 1049 photons divided by S. This gives an estimate of the number of ionizing photons. Let's now estimate NH. For NH equals 5,000 divided by cm3. The nebula is relatively dense, and the Strömgren radius is roughly equal to 0.3 parsec. This radius depends on the number of stars in the nebula, but typically the Strömgren radius is about 0.1 to 100 parsec. For a typical nebula in the Milky Way, ionized by a small stellar cluster. This is the order of magnitude of the size of ionized nebulae that can be found in the Milky Way, or in galaxies in general. This is a wonderful example of a nebula illustrating the Strömgren sphere, NGC 602, in the small Magellanic Cloud, which is a satellite galaxy of our galaxy. Here one can see a group of blue stars in the center of the nebula that ionizes the gas as far as 50 parsec from the center. This does not imply that the nebula has its limit at 50 parsec and that there is no gas further away. What it means is that the photon flux produced by the stars in the center of the nebula is not able to ionize the gas further away than the Strömgren radius. Now we will look closer at the dust absorption. Here you can see schematically represented some dust grains with sizes much larger than the atoms or molecules. It can be compared to the dust that is on a table when one does not clean at its place, or to the chalk left on the blackboard, for example. Let's take a volume element that is characterized by the length, input and output surfaces, and the density taken in the following way. This is the numerical density, not the mass density. So it gives the number of dust grains per unit volume. One can see clearly that each dust grain obscures the light that enters the volume element. Each dust grain has a cross-section that obscures a surface, dA. This allows the determination of the extinction coefficient that is simply equal to, if r is the grain radius, the cross-section of the dust grains. Now, it is possible to estimate the fraction of the surface dA screened by all the dust grains. This would be simply dt, the number of the particles in the box, times the cross-section, which we have called the extinction coefficient. So dt is equal to n times dA times d1, where 1 is the cylinder volume, times the cross-section over the total surface. If this expression is simplified, one has the extinction coefficient times the density times the element d1. This will be called the optical depth T. This is a dimensionless quantity that depends on distances. One can already see that T max equals 1 corresponds to full extinction, because the obscured surface is equal to dA. And so all the radiation is absorbed. This is the definition of the optical depth. Let's see how to use it in order to estimate the fraction of flux that is lost if we have the incident flux here in a given volume. F is the outgoing flux that is equal to F plus dF. F can be negative, and will be in this case, as there is absorption. dF equals F times dt. dt is the optical depth. Or, as it was called earlier, the fraction of the flux that is lost. There is a minus sign because of the losses. And so dF divided by F equals minus dt. This is a simple equation for which the solution can be written as an exponential with boundary condition that is simply the incident flux. The outgoing flux varies with respect to the incident flux. T is the integral from 0 to the distance of the observer. So it can be integrated along the line of sight up to the star at some distance d. Here we have n times the extinction coefficient times d1. If we assume that there is on average n particles along the line of sight, we can simplify this expression. T would be n means times the extinction coefficient times the distance. This is the result of the integral with the assumption that the number of particles can be approximated by some mean value from the distance 0 to the observed object at some distance d. So the integration is made from one volume element to another. The integration of the flux that is lost by a volume element because of the dust grains between the source and the observer. The fraction of the flux that is lost is called the extinction. Rewriting the resulting formula, F depends on the distance of the observed object, so that Fd equals F0 times E Td. Let's try to illustrate that on a graph. It is simply an exponential curve. The y-axis represents the flux, and the x-axis the distance. At distance 0, the flux is equal to F0. This is the condition given in the formula. When t equals 0, the exponent is equal to 1. So F equals F0. Then the flux is exponentially decreasing. At some distance d, we have Td. When t equals 1, the flux is equal to F0 divided by E, which means that 1 divided by E times the flux F0 is lost up to the optical path equal to 1. Astrophysicists prefer to use magnitudes. Let's take its definition. Observed magnitude minus the intrinsic magnitude before the absorption caused by the dust, along the line of sight from 0 to the distance d. This is a situation in which, along the line of sight, between the observer and a star, there is dust in cylinders, in nebulae, etc. One has to integrate the absorption along the line of sight, up to some distance d. Thus, m minus m0 equals 2.5 times 1 og fd divided by f0. Using the equation formulated before, this is equal to 2.5 times d. But one has to pay attention to 1 og e. This is a decimal logarithm and not a natural logarithm. One can see that m minus m0 is positive, what implies that m is greater than m0. Remember that the magnitude scale is logarithmic. There is a minus sign here, meaning that the observed source is seen with apparent magnitude greater than m0, which is the intrinsic magnitude before the absorption. This signifies that the source has been absorbed, and so fainter than the original. We have just talked about absorption, but this is not the only effect present in a volume element. Some photons that will be absorbed, some can be reflected back to the source, some reflected in an arbitrary direction. This extremely important effect is called scattering. This effect will not be described here in details. It will be qualitatively shown how scattering depends on the particle's radii. There are two types of scattering. When photons propagate through dust, they are scattered in the same way fog would do. The first type of scattering is the Mie scattering. It takes place when the radius of the grains is much larger than the photon's wavelength. In this case, the extinction coefficient is equal to the one given by the Mie scattering, which is proportional to lambda minus 1. Another property that is this type of scattering is directional. It is not isotropic. It means that photons do not scatter in a random direction. They rather scatter in a direction that lies closer to the incidence direction. This is the Mie scattering. Another type of scattering is the Rayleigh scattering. That takes place when the medium consists of small particles, smaller than the wavelength. For this type of scattering, the extinction coefficient depends even stronger on the wavelength, as lambda minus 4. Rayleigh scattering is isotropic. In conclusion, if light is scattered by large grains, the scattering is directional and is more efficient for shorter wavelengths. The dependence law is lambda minus 1. The Rayleigh scattering arises for small particles. It is isotropic. It also depends on the wavelength. It is more effective for the blue light than for the red light because of the dependence of the extinction coefficient as lambda minus 4. Both types of scattering are more effective for shorter wavelengths. The consequence of the scattering can be observed on Earth. Both types of scattering can be noticed on this slide. Firstly, the scattering that makes the sky blue. This is the scattering by atoms, so all the particles, whose radius is very small, compared to the wavelength. The wavelength is of the order of hundreds or thousands of angstrom. Obviously, it is the case of the Rayleigh scattering. That is isotropic. It was said that the scattering is more effective for the bluer light. This is the reason why the sky is blue and why there are no visible structures. The uniform blue color is caused by the isotropic property. Now, what happens in the cloud? The cloud is composed of water drops. So here we can find droplets of water.
avec le rayon des grains
With radii,
qui cette fois-ci est beaucoup plus grand que la longueur d'onde et donc
much larger than the wavelength. In this case, the leading process is the scattering, that is directional. This is the reason why one can see obvious structures in the cloud. If the scattering was isotropic, the structures would not be visible in the clouds. It works in the same way for nebulae that are also clouds. Here is a reflection nebula, M78 in the constellation of Orion, reflection or diffusion nebula. It is basically the same. In the center of the nebula, there are stars. One can find some dusty regions that absorb light. There will be an extinction coefficient is related to these areas. There are also some areas where the light is scattered. How to see this in practice? The spectrum of a star is a black body spectrum. The spectrum of a nebula should be composed of emission lines because of atoms that can be ionized by stars. After the ionization, they recombine and generate emission lines. But this is not the case here. Those stars are not able to ionize the surrounding matter. Instead, the light is scattered. If the spectrum was taken in this area, it would be a black body spectrum. The same spectrum that the one of the stars illuminating the matter around them. That is why obtaining spectra of astronomical objects is so important. If one has a spectrum that shows lines, the effects present in the nebula are not the same as for the nebula that has a black body spectrum. In the latter case, there is light scattering, while in the former case, atoms are ionized and then they recombine. What is the final balance between the different processes? In the nebula, there is light scattering and the absorption, that both are more effective for shorter wavelengths. That implies two things. The first one, the absorption is responsible for the fact that the observer sees a source weaker, as if it was emitting less light. Also, if the light is absorbed or scattered more effectively for shorter wavelengths, it implies that sources observed through dust are reddened. This is the interstellar and intergalactic reddening. This was the first conclusion. Now, if one wants to observe sources whose light is strongly absorbed, the observations must be done in the infrared. Light with longer wavelength propagates through matter more easily. The observations are not so simple, because it may happen that the source does not emit light at longer wavelengths. One has to adapt the means to the goal of the observations, at least as far as observations through dust is concerned. Let's look at the quantitative description of reddening and its influence magnitudes. It was said that the color of objects is measured using the color index, the intrinsic index. It will be called B minus V 0 and is equal to B0 minus V0. B is linked to B0 through absorption, which can be in turn expressed as an optical depth. This is for the blue filter. Now for the V filter, which is redder than B, one has two magnitudes. Both are affected by absorption. Subtracting one equation from the other gives B minus V equals B minus V 0 minus AV minus AB. With AB greater than AV because the blue light is absorbed stronger, as it was seen before. This equation can be rewritten as B minus V 0 minus a new term, E B minus V, that is used to characterize the reddening of stars. E B minus V is the color excess. B minus V greater than B minus V 0, because AB greater than AV. It was shown that larger color indices correspond to red stars. Smaller color indices correspond to bluer stars, provided that the bluer filter is placed on the left side of the index. The observed index is greater than the intrinsic index, what implies that the observed source is reddened. Thanks to the color indices and to the color excess, it is possible to quantify the way in which the stellar objects are reddened by dust in the interstellar and intergalactic medium. A direct illustration of this effect, a nebula. In fact, a cloud composed of dust, seen at different wavelengths. This image corresponds to the optical wavelength, the limit in the blue light. This image was taken in near infrared. The wavelengths increases in this way across the slide. This is the infrared image. One can easily see that in the image with the dust, all the radiation from the background is blocked and scattered by the dust. It is lost. It does not reach the observer. When going further in the near infrared, one can see more and more stars near the edge of the nebula. One can see more and more stars. One can see more and more stars when going to the center, even more at longer wavelengths. In this image, almost all the stars can be seen through the dust. This is a cloud of dust in the Milky Way. Barnard 68 that can be delimited in this way. This is an image in false color, with the visible light in the blue channel, the near infrared in the green channel. And the infrared in the red channel. Looking at this image, one can at once see a large cloud of dust located along the line of sight to the observer. Light constantly interacts with matter. Thanks to these interactions, the analysis of the light gives us valuable information. The last two lectures showed that this analysis is quite delicate. All the physical processes at play must be taken into account simultaneously. Continuous absorption or absorption lines, continuous emission or emission lines, chromatic absorption, reflection, scattering, which, in fact, is also a chromatic phenomenon. Also, one needs to consider chromatic effects caused by the Doppler effect, rotation, thermal agitation of molecules that sometimes broaden the emission and absorption lines. All these phenomena play a role at some point, an important role in our understanding of astronomical objects.